Welcome back to Lawrence Tech. I'm Jim Kearns, and today we have yet another exciting episode in our EGE 2013 static series. Today we're going to be looking at the internal loads in a beam. So it's kind of a switch from previous topics where we looked at just reaction forces and moments and applied forces. Here we're going to actually look inside the beam and see what the forces are inside. So it's a simple case here. We're going to take a simple beam with a single load in the middle. It's 10 meters long. There's reaction forces on each end. And we'll use the method of sections where we cut the beam in a section. And if the beam is assumed to be in static equilibrium, then a section of the beam has to be in static equilibrium, which means that there have to be some forces applied at this cut to keep it in equilibrium. There'll be a shear force, there'll be a bending moment, and potentially a normal force there at that cut. So we'll go through the method for determining it in this simple case. So here's our beam. It's 10 meters long. We've got a 200 Newton force applied in the center, and by inspection we can see that we have 100 Newton reaction forces at each end. If I cut that into sections, I can take a piece of that beam, again as I mentioned, and I've cut it at some distance x, and I want to be able to determine the forces at that section, the shear, the moment, and the normal. And of course, on the other side of the beam, the remaining section, we have the equal and opposite forces to maintain this portion in equilibrium. So I can work from either direction, but for today we'll work from the left end, and we'll calculate each of those forces as we go. But before we go off into forces, I should comment on the sign conventions. We have a beam cut into three pieces, kind of a left, a center, and a right section, and we have the shear forces drawn and for each of these, and there too. And we have the moments, and we have the normal forces, and these are all drawn in the positive direction, assuming our positive sign conventions. And if we look at, a matching pair here, we can see that the forces are all drawn opposite, okay, once they're cut in sections and they're exposed, but internally they have to be the same value. If I have a beam and I have an internal shear force inside the beam somewhere, at this point, that has a single, we'll assume for a moment, positive value, and when I cut that off, I have a positive shear, but for the two pieces, well, I should cut it off here or actually cut it, right? For these two pieces, for them to be as they touch, we have to draw those forces in equal and opposite directions to satisfy Newton's laws. But as they're drawn, as I mentioned, these are all positive forces, so our convention says that any normal force resulting in tension is a positive force. So all these are positive normal forces. We say that a shear force that rotates the beam segment clockwise is positive. So in this case, I have a force like that would cause this segment to rotate clockwise. That's positive. This force here pointing up would rotate it clockwise. That's positive. This pair of forces, again, clockwise, again, positive. Okay? And then for our moments, we say anything that bends a segment concave upward is positive. So if I'm, by that I mean if we're bending a segment like this, we have a moment applied that way and a moment applied that way, that gives us our concave upward direction, or if you prefer, a smiley face. Here we have a section of the beam to the left of the applied force. So this x right here is less than 5 meters, okay? And we can find out what the forces are through our equations of equilibrium. So by inspection, I see there is no applied force in the x direction here. By inspection, I can say I can determine that the normal force is equal to 0 in this case. If I do the sum of the forces in the y direction, I get my 100 Newton force up. I'm assuming there is a shear force acting downward. If I solve for my shear force, I get V equals 100 newtons downward in the way that I've drawn it is downward. I get but if we think of our sign convention, positive shear force results in a rotation clockwise. This downward force is going to tend to cause that beam to rotate clockwise. So that is indeed a positive shear force. Now, if we consider our moment, some of the moments, and we'll take the moments at our section here, so we don't have to worry about what the shear force is. We can only work with the known reaction force, and we solve directly for the moment at that section. So the sum of the moments at our section x equals 0, and that's equal to minus 100 times the distance x plus that moment at x. And we know that we've drawn a positive moment here, and that the moment on the other end has to be negative to be equal and opposite for this to be in equilibrium. So our moment at x is equal to 100 times x, and that's Newton meters is our units. And we can calculate a couple values. If our x equals 0, our moment is equal to 0, and that makes sense. When you're right at the end, there's no leverage, you don't get any bending. X equals 2.5, our moment is going to be equal to 250. If x equals 5 meters, our moment equals 500 Newton meters. So at any point now to the left of that 5-meter point, we can calculate what our moment needs to be. And on the next slide, here is a plot of that moment. And I'll point out that from this left edge all the way over here to our section, there are no forces applied, okay? There's no change in force. So our shear force is constant. There's no change in shear because there's no change in force. And our shear force is a constant positive value, and we look at the moment, and this moment has a constant positive slope. And as it turns out, we can find the shear force by integrating the load across that section. We can find the moment by integrating the shear force. But we'll do that in another video, go into those details. But I'll just mention that for now as a way to kind of look at things and say, does this make sense? You know, if my shear force was 0, how could my moment be changing or whatever? But that constant positive shear force results in a constant positive slope on the moment. Now here we're taking a section over here to the right of that applied force, so x is greater than 5, and I'm going to ignore x exactly equal to 5 for just the moment, okay? Again, our normal force is 0 by inspection. So if we look at the sum of the forces in the y direction, that's equal to 0 for equilibrium. And we have our 100 newtons minus the 200 Newton applied load minus our shear force V we've got drawn pointed downward. If I solve for V, I get V equals minus 100. Now I drew the arrow in the positive sense for our shear by our sign convention. And if we look at this, we got a negative value for V, so the actual force must be pointing upwards. And an upwards pointing force there will result in a counterclockwise rotation. So that is indeed a negative shear force because it gives us that counterclockwise rotation according to our sign convention. Again, take the moments at our section. sum of the moments at x equals 0, and that's equal to our 1 minus 100 times x. Then we have plus 200, our applied force, times x minus 5, which is the distance from here to here, which is the distance from the force to the end. If this is x, this is 5 meters here, and this remainder is x minus 5, plus our moment. We can solve for our moment is equal to minus 100x plus 1,000 Newton meters. And we get the, again at a couple points at x approximately equal to 5, I get a moment equal to 500 or thereabouts. At x equals 10, I get a moment equals 0. And again, if we think of our sign conventions, if I look at how this moment is bending that beam, it's concave upwards, so yes, it is a positive number. And here's a plot of our results so far. The blue lines are the results from the forces to the left, or the calculations to the left of our applied force. The red lines are for the new stuff that we just did on the right half. And if you'll notice, in our shear force, there's a discontinuity here at x equals 5, and that discontinuity is equal to 200 newtons, and that's again our applied force. So that discontinuous force, that point force that we applied of 200 newtons, gives us a discontinuity in our shear diagram equal to that. And we go from positive 100 to negative 100 in our shear. Our moment, where the shear was positive and constant, had a positive constant slope of 100. And then once we cross that discontinuity, there's a discontinuity in the slope, but not in the actual value. And it now has a positive negative slope of negative 100 newtons per meter. And if we were to do an integration over this curve here of that, we get that shape below where it goes up and then it comes back down with no discontinuity in the actual results. So that's consistent with our sign conventions. It's consistent with what you expect if you integrate. So I think we got it. I think we really did it right. Now, as I mentioned before, we could have done this whole exercise from the right. The math would have been slightly messier, but not awful. We just have to use a 10 minus x instead of we used x, and we'll leave that as an exercise for the reader. Okay, so I hope you found this helpful. We'll do some more examples with some distributed loads, and we'll get into the actual integration process and do it mathematically that way in a later video. But for now, that's it. Thanks for watching, and I'll catch you on the flip side.